Okay, hello everyone. Uh, Today I have a repeat of the seminar of the lecture I gave at Joker 2021 conference and about mathematical architecture in Kotlin. And today it is in English and it's slightly with a slightly different accent since we do not have to tell people basic things about mathematics, and I expect all the people here will know what I'm talking about. So I will focus on some more detailed things, and maybe we will even have time for a small demonstration about different things. And today, our host today is Yaroslav Postavalov, and of course you
Hello.
will. Hello, and of course you are welcome to ask questions, interrupt me, and ask questions about what I am talking right now. And also, please notify me if something is wrong with the presentation or whatever. Well, so let's begin. And if you don't, in case you do not know me, I'm Alexander Nozick, and I'm team lead at JetBrains Research and Nuclear Physics and Methods Laboratory, and also at MIT. And again, this talk was originally prepared for Joker conference. Oops. So the first thing I had to explain is why do we need math? Because everybody knows that we need our programming tools just to place JSONs from the database to the user and nothing else. Of course, it is not correct, and we need mathematics for a lot of things. For example, of course, the classical thing we need to separate cats from dogs via neural networks, and it's a quite modern usage. And uh, it's not all we need math for, and we need a lot of other usages as well. For example, in my task until recently, now as well, was to measure the mass of neutrino. And for that, of course, you need mathematics. You need
Mm, I'm sorry, I don't see any screen share or presentation.
Oh, okay. It was my problem. You should have asked this sooner because I forgot to share the
Mm.
screen for their Google Meet as well. Yes, yes, yes. Sorry. Now it should be fine. Please confirm.
Yeah, it is. It is.
Okay, the first slide, then again, I am repeating it again. It's just introduction. And here we can have these cats and dogs here, and we have a choice mass experiment, my home experiment where I made my PhD. Uh, and it's an example of things we need to calculate, some multiple integrals and other things as well. Of course, we need a lot of other practical things, more practical than the neutrino. We need to launch a satellite, we need to control its orbit, and a lot of other things. And even more practical for us, it's distribute electrical power. For example, this task is solved by our partner Fabric Electric and other people as well. So we do need mathematics, and I think it is obvious. But actually, when we start to talk about mathematics, there are two different things people think about when they say mathematics in programming. And it's uh, abstract mathematics, something which is the language of the mathematics, which is very good, abstract, and well understood by mathematicians, but we do not have proper tools to work with it. So you can't just enter the formula to the computer and expect it to compute correct. And on the other hand, we have a very low-level numerical algorithms, numerical tools, which communicates very good with the hardware, but do not work well with mathematical abstractions. So those are two languages. And we have what Julia people call the two-language problem. Uh, and the question is if we can create a language which is good at both, or we forever are doomed to make a translation from one language to another language. But before we go into that, we need to understand what is the number or a number. And this question is quite old. You see here this guy, it's a Pythagoras, uh, who was one of the first who asked this question. What is the number? Is it integer or it's a rational or whatever? By the way, Pythagoras did not believe in irrational numbers. He knew about them, but he thought that they're something demonic or something like that. And the problem that is when you ask different people in different situations, you will get a different answer. From the simple mathematical point of view, this thing is simple, but from the computer point of view, not so simple, because you can answer this, but then you will be asked this, and is the result the same, or it is different? In computer, in most cases, it could be different. For example, if you use this expression in Java or Kotlin, you will have integer here and floating point here. So it's not obvious. But then you will have some even more complicated problems because things like these are obvious in our abstract mathematics, but not obvious in computer mathematics. You can try to do that and you will be a little bit surprised by the result. And when you will be surprised, you can Google this thing here, EAE 754, and understand why the answer is not so obvious one. And then we get further and we get into the region where we do not have any clear definitions. This one does not make any sense from the classical mathematical point of view because we are summing oranges and apples to different types of objects. But if you do that in NumPy, for example, you will get the result. And people who have a lot of experience with the NumPy and with tensor algebras expect this thing just to work. Additionally, we can work with matrices, and here we have even harder problem because we can treat this number 2 as a identity matrix multiplied by 2, or we can treat it as identity tensor, and the result will be different because identity matrix has diagonal elements but does not have non-diagonal elements, and identity tensor has this one in all fields. So result will be different depending on what do you expect. Then we have even more complicated things because we want to work with the functions, and this thing you usually can do, for example, in NumPy. But as a mathematicians, we probably want to do that. We just want to add numbers to functions, to polynomials. And that will also depend on what you mean by number and what context, in which context you operate. And of course, there are some more bizarre things like sine functions from tensors or whatever. As an example, not from mathematics, but from our real life, well, more or less real life, is relativity. I'm a physicist, so I'm taking examples from physics. And in physics, you probably know that your rules of geometry and the sum of angles of triangle is pi, or 180 degrees, and this your universe is more or less flat. But actually, we know that in curved space, which we should which we are live in because gravity curves the space, the plus works the same way as in Euclidean space in the flat space, but vector multiplication dot product works differently. So it will have some changes to the rules applied to these operations. And actually, what I've already said, trigonometrical operation will work a little bit different. And if we want to make computations in non-Euclidean spaces, then we need to introduce complete new set of operations. Okay. Now the question what we want from numbers, and we want several things which are not always could be achieved together. We need intuitive operations, so we need to intuitively understand what we are doing from our mathematical point of view. We want after NumPy, of course, there are always epoch before NumPy and the epoch after NumPy. After NumPy, we usually want mathematical propagation of operations because we want to do the same operations we do on numbers with vectors, matrices, tensors, whatever. Why we do that is a good question. If anyone is not sure why we need that, please ask a question. I will answer. And we want some kind of consistency. We want to have a type safety or compile time safety, so we won't be able to operate on incompatible numbers. This is not the case in NumPy. In NumPy in Python, you will have a runtime error in most of cases, and it's a problem. And that is this thing we definitely do not want in modern software. We want fail fast behavior, whatever we can get it. Again, there is an old problem of performance, and when we talk about computations, people usually immediately ask us about how fast it is. So we need to for our mathematics to be relatively fast. Relative is important because it's not possible to achieve absolute performance. And let's see what are the problems with the performance. For example, let's see an example, a typical example. It's in Kotlin, of course, but you will see the same kind of example in any language, including Python. People are just, here is a simple thing. You need just create a list of numbers and then increase each one in this list by one. It's a very bad solution, and let's see why. Because first of all, list is not effective for holding primitives because of boxing. Again, if you do not know what boxing is, I will explain it a little bit later, or you can ask a question. Adding elements one by one causes multiple array copies in this case. If you know how Java array list works, it creates a small array, and then when you add additional element, and if it exceeds the size of initial array, it creates a copy of array and copies of all of the elements to the new array. So in this case, it will be like 3 additional array copies, which is not effective. And of course, you will have an unboxing and boxing on each of these operations. In this regard, Kotlin is a little bit worse than Java, not in terms of peak performance, but in terms of performance pitfalls, because if you do not know how those lambdas works, you can get the bad performance. what we can do to improve that, we can use arrays instead of lists, and still we should not use map function, which is idiomatic. This code here is idiomatic in Kotlin, but it is not the most performant one because still there still is boxing here on this map operation. So the best way to do it in Kotlin performantly is to do it this way. And this is just an example of how not the language affects performance, but what you are doing affects performance. And usually, of course, we want not to think about the performance of things we do and just that our library and our framework do it the best way. Uh, and here is the boxing, and this is the major problem for today high-level languages. The boxing is the most important problem in terms of performance, and when they have a collection, so-called box collections, typical list, either Kotlin list or Python list or Java list or whatever, we just have a list of references, and each of these references points to the item in the heap space. And so each set or get operation on this element will involve additional memory operation, which are much slower than just take a number from the memory directly. And if we use a specialized arrays, it's not a problem because all those elements are allocated directly in this memory block and do not have to involve heap to do that. Also, it is not only memory operation, but also, which is probably more important because memory operations nowadays are pretty fast. It's problem of processor cache. So if you want something to work really fast, you need to upload it to the processor cache ahead of time, and then the operation will take this item here, not from memory, but directly from the processor cache. And those things you need to think about if you want to do a performant code. So you need specialization because this thing I showed here, you can't achieve it without knowing exactly which type of element you have here, what is the length of it, 4 bytes, 8 bytes, whatever, and how can you read it. So you need to use a specialization. And for specialization is good, but then you need to repeat all those operations, all your complicated mathematical operations on each specialized type. This is a static polymorphic specialization. Types are known in compiled time, and you need to use a specialized version of containers like int array, double array, whatever. And there is another solution. This one, by the way, is used in C, in NumPy and Multic, we'll see it later, and most other systems. Another way is to infer the type dynamically and just create some generic algorithms and then infer the bottleneck, the slowest thing point in this algorithm, and use specialized versions of operations just in this place. The problem with this dynamic approach is that it works only for known types. You can't dynamically use a specialized version of container and operation if you do not know the type ahead of time. Okay, we will probably return to this later. Now let's see how this is approached in different languages. So in pure Python, we do not have any specializations. Pure Python is very slow from the performance point of view, and another thing which is important: how do we infer how operations work? In Python, operations are bound to objects, not to types, but to objects. So each object could have its own operations, and the type of operation is inferred by what type of object calls it. In NumPy, they add dynamic specialization on top of that, because in NumPy you can create an array of, say, float numbers, and then you can create a function which works with the nd array of any numbers, and then it will decide which low-level, C functions to call for this array depending on the type of the array. Of course, it will fail in runtime if the type is not recognized. In C++, they mostly use static specialization, which are patterns, templates, and templates are compiled statically. So when you compile a program, you know exactly which types do you use, and so it could be optimized. This is the reason that C++ is considered fast thing, because when you compile a program in C++, you know the types, so you can optimize for those types. But this actually could be achieved in other ways too. Operations in C++ are bound to types, not to objects, which is probably good, and resolved also in compile time. Julia have a little bit of both worlds, because in Julia there is no static compilation and all functions are compiled just in time when they are called with the exact types. And so it's a little bit of both. It's a dynamic specialization, but it's actually it's compiled in runtime. So yeah, on one hand it's dynamic, on the other hand it is compiled, so some optimizations for specific types could be made. Java does not have a lot of space for specialization. There are libraries which do dynamic specialization, which infer the type of container, like array or list, being passed, and then optimize it. But otherwise, in core Java, we do not have any tools to work with mathematical objects. Of course, there's a lot of libraries, and there are no operations on write in Java at all. In Kotlin, actually, we have all things what we need. We can create a dynamic specialization. We can infer the type as we go. We can do operation override, and we actually can do a static specialization with inline functions. Broadcasting is also possible if we want to implement it. Kotlin is very flexible. Maybe not as flexible as C++, but much more flexible than Java. Okay, let's see how we work with arrays in Python style. And in Python style, of course, I mean NumPy. You never work with numbers in pure Python. So in Python, we just create arrays and just do operations on array, because NumPy array have all those operations we need overridden for us, all possible operations, and we get the result. It's pretty straightforward. But of course, you need to remember that NumPy actually is not Python, and NumPy actually have types. And those types are used inside the C code, which is inside NumPy. So, for example, if you set type here, the result will be different. And this is one of the problems with NumPy, that you have implicit types. actually. And you can see that the function actually called in NumPy is a C function, which calls compiled code in C. As I said, Python dynamically infers a C type. If you do not set it explicitly, it infers it and uses its best guess to operate. But after that, operations themselves are specialized and pretty fast. And what is important for NumPy is that all Python numeric libraries are using NumPy or at least NumPy compatible. So it's not just the convention for other libraries. It's a foundation for other libraries, and this is important for our talk later. Uh, we're coming to Kotlin libraries, and here is a multic by JetBrains, and you can try this link in Datalore and play with it a bit. Multic is made just like NumPy. In in this regard, is somehow a copy of NumPy. It's made so people from Python would be comfortable with it, and it does exactly the same. The difference is that you have explicit types and you can check them, and the operations are resolved. I mean, the types are for those things are resolved half in compile time, because here we obviously have an array of doubles, and the operations are half compile time, half runtime. So the types of arrays are resolved in the runtime, but the operations are bound by types. Here you see that this operation works explicitly on a specific type of numbers. Uh, inside you will see inside the multic, if you I'm not sure, it could be changed a bit because I've made this talk like several months ago, and it's changes in the time. But if you see inside, you will see that multic, like NumPy, multic have a specialized version of all operations hard coded inside for each type. So you infer the type and then you use a specialized version of operation. There are good things and bad things. It works only on multi-arrays, of course. It has multiple backends, and right now JVM only, but it could both use pure Java, pure Kotlin, pure JVM implementation, which is maybe not as fast for complicated things, but very fast in terms of memory access. Uh, and it has a backend with C bindings, like I'm not sure. I think it's a BLAS there. It uses BLAS under the hood. So it has bindings for hard operations like matrix conversion and multiplication. Uh, for them, it automatically switches to native implementation, which is optimized uh, for the hardware. And this is why it is fast. It's fast not because it's written in C, but because it's optimized for the hardware. And what are problems? That this is limited to basic types plus complex. You see here there's a binding for complex values, and it is not compatible with other existing libraries. So multic, like NumPy, is designed the way that you need create all your libraries based on multic. What about other libraries I've mentioned? And there is a huge library, Apache Commons Math. It's very extensive. It has a lot of things, but it's not very it's not quite optimized, so it's not the fastest thing there. It has a lot of things, but the performance maybe not the top one. YGML is a specialized library for matrix pure JVM implementation of matrix operation. It's faster than the common smart, but I think it's deprecated right now, so I'm not sure it's support it's developed anymore. Ojalgo is a number of algorithms which at least it says that it's super fast and that's it's again it's pure Java implementation, but and its author says that the performance is similar to the optimized native libraries. We have not checked it, but I think there is a truth, at least some truth in this regard. And D4J is again it's one of attempts to do something like NumPy in Java, and it uses native bindings, but I do not see a lot of development there either right now. And of course, there are some libraries in Kotlin right now. It's a comma. It's one of the first attempts to do something like NumPy in Kotlin, and it came out, which is our library. So I mostly will be talking about it today. And Multic I mentioned already. KMath also began when we started to work on KMath like 2 or 3 years ago. We also thought that I also thought that we will be doing something similar to NumPy, but it soon became apparent that it is not a good idea. So that we could do something much better in Kotlin. At least it is my belief. Multic again uses a NumPy-like approach, so maybe both approaches have its their merits. Okay, now we're deeping into the algebra, and we are talking about how to solve the problem I stated above, how to make abstractions which will allow us to be flexible and fast and effective at the same time. And we have one such thing in mathematics already. It's called algebra. Algebra is actually an interface for operations. And now, and I'm not the one who invented it. In Commons Math, they use algebra to abstract operations. But since in Java they do not have operation overrides, it is not very convenient to use operation abstractions in Java. And you can see here some kind of scheme from Wikipedia about how different algebra relate to each other. And we have groups which have a plus, minus, and neutral operation, ring which have a multiplication, and field which have a plus, minus, multiplication, division. And an example how it is done in Commons Math. Of course, we can't achieve full coincidence between mathematical abstractions, mathematical algebras, and our computational algebras. So there is little bit distinction, but in general, we try to follow mathematical ideas later. So how does it work? Yes, again, an example from Commons Math, and again the tag for Detalore. You can play with it, and you can see that yeah, we can do abstraction. We can do an abstract function which works in any algebra. It's pretty nice, but the notation for the function is not nice because we need to chain operations instead of writing them in a mathematical way. And how to fix it? In KMath, as I said, we use those algebras. And for example, here is a group which defines add operation, and somewhere here, here it is. It defines also neutral operation. So group operations, it's a group without zero, and group is a full group which involves all operations. We need these distinctions, for example, for tensor operation because it's not clear. You can operate tensors, but you do not know which one of them is a zero tensor. because if the group does not know the size, you can't create a zero tensor if you do not know the size of the tensor. So we need this distinction. And then we create ring operations and rings on top of groups. So an example of ring is integer numbers or long numbers or short numbers. Yeah, for example. And what is the important thing? It's a different from C++ and from Python is that we define operations not on type, which involves those operations, but on the scope in which these operations are done. You can see here it's an extension function. So inside the scope of this algebra, we will have those operations. And they can even be different. Of course, we can override the operations for doubles and integers, but we can have a different sets of operations for our types like matrices, vectors, arrays, etc. This is the idea. Again, this idea will be much more productive with the multi-receivers or context receivers, which will come very soon, as you probably know. Kotlin features a prototype for context receivers in 1.6.20, which will arrive in a very short time. It's already available in custom builds. And so in this case, it is even more simplified because our interface now have only one method, and all those things we can add uh, as an extension function, as extension functions. And what is more important in this thing I'm showing you is that those extensions are dispatched statically, so we can use optimized versions for those operations. I mean, compile time optimized versions, and they will work only in their scope. So you can uh, add two doubles in a double scope, it will work one way, and add double to complex in the complex scope, and it will work another way. And this is the
I
idea.
must I have to notice that the syntax on this slide is not actually in Kotlin. I mean, it is hypothetical.
I
Mm.
think it is. I think it is more or less final because I saw the final proposal for context receivers, which is
Yeah,
that.
I've seen the final state of that issue, but I just must notice that
Yeah, yeah. It's not. It's
just
not. It's not
you can't
still.
just compile this code by the released version of compiler.
Yeah, yeah. It's not. It's not published yet. It's like hypothetical, but it's very close to the one they pushed to 1.6.20. Save for maybe some things like the order of types, but I think it's the same as well. Uh, mm, yeah, yeah. So, all those things I said as well, and there are some additional optimization because extensions are dispatched in compile time. We can have a lot of optimization, specializations, and etc. By using those things. We can even overwrite one extension with another, but it's a bit tricky. Okay, the second thing I said is algebra propagation. Why we need algebra at all? Because we want to add buffers or tensors the same way we add numbers. And if we want to add sum to tensors, we either need to override those sum operations for each tensor type, or we can take a rule for adding numbers as an argument, like it's done here. If you have an element algebra, if you can sum two elements, then you can add two buffers. Oh, of course, in Kotlin you also need a factory for the instance. In Scala or C Sharp, it could be done. It could be avoided with implicits, but I do not like implicits. I like passing this factory explicitly. So yeah, when we have element algebra, we can automatically construct a buffer algebra. Buffer is a linear structure like array or list. We need to introduce it because arrays are incompatible with lists. And from those, you can create in an many-dimensional algebra or something more complicated. Also, of course, we need some kind of optimizations. So let me I forget what this example is about. Okay, yeah. The important thing is that some operations will be very effective when you do it on a specific data layout. I mean, layout in memory in terms of access, etc. And it could be done by dynamically specializing your structures. For example, you need something to do fast, then you just check. In C++, you can't, without a lot of effort, check the type of incoming variable. But in Java, Kotlin, JVM, and even in Kotlin Native and other things, you can do that. So you are checking the type of structure you're using, and then if the type is all right, you do nothing, and it's free. And if the type is wrong, you do inline conversion. In this case, you do this conversion at most once, and it is done automatically. You do not need to think about it. And then of course, you can use optimized version of this structure. And if the incoming type is a correct one, it will be super fast. If the incoming type is wrong, it will be converted. But now you need to remember that we are working with the scopes. So all structures produced inside the scope are automatically of the correct type. So you need to convert it only once, at most once. When the variable enters the scope, it is converted to the format it scopes likes. And then you will have a very fast free operation. And what is important, you can operate on the structures produced by different scopes. For example, in this example, we have a structure produced by Victor, JetBrains Victor library, which is created to make high performance operations on with automatic vectorization, and Commons Math version. And you can mix them together, and you can use them without any explicit conversions. They are converted automatically to the same shape, to the same format, which is pretty flexible and in fact pretty fast if you do not abuse this feature. A more complex example here, I probably will skip it because I'm talking a lot already. But you can work with a complex, you can make operations with a complex vectors, and then you can work with a complex many-dimensional structures like this. In the end, the operation looks like in NumPy, but since we explicitly entered the scope, we know the type. From the scope, we can understand which types of object we are working. We can't use this expression outside of the scope, this is the important. And it will be year and compile time year if we try to add two complex index structures outside the scope where operations are defined. Okay, as I said, we have several core algebras. If we have time, I will show you an example. But basically, we can operate on buffers, we can operate on many-dimensional algebra, and of course, we have some linear algebra operations. As I said, it's a little bit in things like NumPy, they're the same, and many-dimensional algebra and linear algebra, I mean. But in fact, in my experience, a little bit different. As I said earlier, you can, for example, multiply tensors, but in terms of matrices, matrix multiplication does not make any sense. You have a dot operation on matrix, which is a Cartesian product, but multiplication does not make any sense. So yeah, I would like to separate um, tensor operation from linear algebra operation. I'm not sure it is convenient, but it's a point of discussion. And of course, we have a tensor, and for right now we have a experimental TensorFlow support, and I believe that Roland was working on the PyTorch, and sometimes in future he will finish. And of course, we have integration. As I said, since KMath is not implementation, KMath is API. This means that we can integrate with different libraries, just creating very thin wrappers for them and integrating them into the single, into combine them together in this single expressions, which is my idea. A quick, very quick thing. I think that we will ask Yaroslav to make additional seminar about expressions later, because it was his idea mostly and his implementation. But we also have expressions, and because we thought, yeah, we have numbers and we have those nice abstractions about numbers. Why can't we operate the same way with expressions like polynomials or functions or whatever? And yes, we found out that we can create algebras for expressions. And it's pretty nice. You can see here there are some limitations, mostly because of type clashes. So sometimes you need to wrap numbers in this number function. But all in all, it's in general, yeah, it's just it's just a simple expression, and you just do it, and you can operate with it, and you can sum them, do operations on them, etc. Divide them, do whatever you want. So numbers are not only numbers, but also all mathematical objects as well. Another thing that we moved even further. So now we have expressions, and it's nice. And functions, they're not very performant, but it's not a problem. Why won't we operate on abstract syntax trees for mathematics? You know, the idea was actually inspired by I forgot the name. Yaroslav, remind me
Mm,
please.
Kotlin you
Yes,
mean?
yes, yes. I forgot the name. I'm bad with names. Yes, it was expired by Kotlin by Brandon. The name is written here. Okay, sorry, Brandon.
Brandon Considine from
Да,
Canada.
да, yeah. Sorry, Brandon. Just your name just left me for a minute. And it's a picture from Brandon's work. And yeah, we can operate on symbols, and we can operate on syntax trees. And this is a very nice example by Yaroslav here, where he just parses this expression and then compiles it to LaTeX. And actually, you can do the same not only to LaTeX, you can compile it to some kind of GPU kernel, or to another language, or to whatever you want. I believe that Yaroslav is now presenting the work where he compiles it to Java bytecode very effectively, and it's work very fast, much faster than the interpreted expression. But I won't uh, spend a lot of time on this right now. We will ask Yaroslav to make additional talk about it. Okay, another, as I already said it. And what is Roland is very exciting about is our automatic differentiation, which also can do the syntax trees, and we can work with automatically differentiable automatic differentiation, whatever. And this picture, I believe, from Eric Mayer's work, where he explains how it works. Another example of algebra. Yeah, it's an example I'm pretty proud of because it's a very simple example where we introduce a matrix function. Matrix function. I'm not sure. I don't believe it's possible in NumPy, but it's possible here because since we can introduce algebra for anything, we can introduce algebra for matrices, and we can do integration of matrix function, and it works. You can check it. It works. So we can introduce algebra on matrices and then do integration in the matrix field, and it works. Matrix ring, not field. It's a ring, and it works. I'm pretty excited about it. Yeah, a lot of algebras because we have wrappers for existing operations. Again, came up with the API, so we are just creating wrappers for libraries and bringing them all together, and they can work together in one environment. A lot of algebras, a lot of all those things are algebras here. Um, Again, let's get back to the performance and spend some time on performance. Uh, what do we need to make mathematics performant? We need avoid boxing. This means specialization. We need to work with a continuous memory layout. So it's cache friendly, and we need it optimized for single instruction, multiple data instructions of the modern processors. How to do that? For In order to avoid boxing, we need to go back and remember the types. Of course, I'm relying on Java types, but it's more or less the same in all languages. And Java to Kotlin type mapping. In Java, it's a double, Kotlin double, and then a double. It's a difference here. In Java, the primitive type is different from the boxed type. In Kotlin, they're the same, and either the type will be boxed will be decided in runtime, not in runtime, during compilation, but it will be inferred. We have a specialized arrays in both languages, and we have actually a difference in how we define functions, because in Kotlin we have a first class functions, but it's a little bit problematic here. Yeah, it's a sad phase because we still need to use specialized versions of arrays. Right now there is no way to automatically specialize arrays, and it's complicates things a lot. And the most complicated thing is here. Just in case if you do not know about it, if you want to make something performant, do not use Kotlin lambdas, at least in case they are not inlined. The problem is that this function here is translated not to the function like this, but to the function with the capital D's here. So
But actually, you can write a function which is similar to the univariate function from the slide by using KT7770. But and I use it for specialized expressions to eliminate boxing overhead at all.
yeah, yeah.
I mean,
GraalVM is also very good with all those things, but you need to be careful. At least you need to be careful with these things, because by default the bytecode here uses boxing. So just a moment, please. I will just turn off the notifications. Yeah, I will just disable the notifications. Oops. Yeah. Again, an example of you need to remember that when you have questions about performance, you need to benchmark, and here is an example of benchmark of dot product operations on different types of matrices. You see, it's pretty straightforward. You just create a algebra for operation like commons math, linear space, linear operation space, Gmail, linear operation space, or whatever. What is important is that you can have different implementations of those operations in the same namespace simultaneously, because they exist only inside the scope of this object. Here we have an automatic conversion to the format, because when the matrix enters the scope, it is automatically implicitly converted to the format which is the most effective for this specific set of operations. But what is important here is, yeah, if we take a basic GDK, as I said earlier, Kmath is an API, but of course we have some basic implementation, um, uh, which we use if we do not use any external connector. And we can see that pretty nice numbers that if we use connector, the performance is quite high. For example, for eGmail, we have a performance like 10 times better than the common math. If we would have a lock on common math, then we could not use it. But now we can, if we need more performance, we just attach the library, which is much faster. But the set phase here, you see that is even our specialized implementation, the score is not very good for our basic implementation. We do not expect it to be super fast, but at least we wanted it to be faster than some other things. And this is very strange, because you can see from the example above that we have a CEM dot with conversion, which involves automatic conversion for each entry. So in order to compute this, we need to convert matrix 1 to commons math and matrix 2 to commons math. And here we do it outside of test. So this one should be much faster. But the benchmark shows it's much slower. I don't know why it is. I really don't know. I tried it multiple times and the result is the same. But yeah, it's some kind of how GVM works. But if we switch to GraalVM, we see a different picture here, and we see that the results, even for commons math, results are better. It's the same machine, of course. For eGmail, results are slightly worse, but more or less the same, it's consistent. But result for this operation is much faster. It's 2 times faster with the commons math. It's very good result, and it's only about 2 times slower when the super fast Gmail, and it is generic. Again, for very simple implementation, not hardware specialized, it is a very good result. And the conclusion is that GVM, you need to select the proper GVM, not just something. First thing you choose in the internet. Okay. The difference, the difference between those two benchmarks, I mean, Liberica and GraalVM, is actually obvious when you try to profile it and you see these things here, and you probably are familiar with these things. It's actually a boxing, and yeah, yeah. Somewhere in our generic algorithm, we still have a boxing, or more specific, yeah, boxing in this case. And what GraalVM does, it just eliminates this boxing. Okay, memory layout, as I already said, memory layout is important, and memory layout is solved by introducing specialized container structures. The generic buffer uses list, and list is not effective. I already told you about it. And for if you want to work with doubles, then we are using the optimized buffer, which inside holds the GVM specialized double ring. But of course, it's not as easy as that, because when you perform a get operation here, if you do it using this specific double buffer, it will be working fast. If you have the code, because it knows that this operation will be inlined, and it will be just a specialized array access. But if you use a generic buffer, which in fact is a double buffer, the operation could be slow, because the result of operation will be boxed or unboxed in this case. So there is a trick for that. The compiler must know the exact type of operation in order to make it fast. So even if you use a specialized version of your container, you still need to make sure that the compiler knows about it. Yeah. Uh, I I do not have time right now to explain how I avoid it, but in general, it's the same trick I showed you about with the structure conversion. We check if the incoming type is a double buffer, and use optimization for double buffer. And if it is not, we use a generic access, which is slower, but it still works. In NumPy or Multic, if you use a type which is not covered by basic types, it will just fail. Okay. Oops. Yeah, it is. Single instruction, multiple data. I'm not sure I should talk a lot about this, because this problem is actually mostly solved right now with the modern GVMs. There is this pretty nice library, Victor, by JetBrains Research, and they do a native optimization of access. But when we compare the implementation, the performance of what Victor does and what modern GVM does, it's more or less the same. So yes, in some corner cases, you still would want to have a manual vectorization, and I should remind you that manual vectorization is available in GDK 17. We have not tried it yet, but it's pretty interesting. But in most cases, automatic vectorization in GVM is already pretty fine. So I don't think it's a huge problem right now. Okay, solutions to performance problem. There are two solutions, as I said earlier. One solution is to use a static specialization. So inline functions, I remind you that in Kotlin, inline functions are computed in compile time. So if you use a generic in inline functions, in most cases it will be substituted by actual type during compilation, so there is no problem with specialization. But of course, you can't make all the program in line. Use extension function, because extensions are statically dispatched. Again, when you use extension, you know the type, the actual type in compile time. So extensions are very neat instrument to work with the performance specific problems. Of course, we can use existing libraries which are very fast and just create wrappers for them, very thin wrappers, color structures and use. And of course, we can use a dynamic specialization as well. For example, you see here the typical method which is used inside the KMath. And actually, a very similar thing is used in Multic as well. So we infer the type of incoming type, and creating a structure based on this type. And if in multi, last option is that we create a boxed structure or non-performant operation. I'm not sure, but I believe in multic it will just fail if you, or if even you can't create structure with a non-supported type, because all generators are type safe. In K-math it will work, but it will work slower, of course. Okay, conclusions. Uh, Kotlin mathematic ecosystem is young, but it is healthy. You can see that there is a number of libraries. They all still in experimental phase, but we can have access to a huge number of Java libraries. And I believe in JavaScript and in future native libraries as well. Right now, it's a little bit of pain to make a bridge to native libraries. Yaroslav can talk about it in the next talk. But again, we already can do a lot of things. And it is my belief that it could rival Python for data science, Julia for computational finance, and C++ for automation. Of course, there's still a lot of work to do. Mostly, we need to provide convenient APIs and convenient tools for people from other systems. The main point of making the completely new foundation for the system, like Maltic tries to do, I mean, library which everyone uses, like NumPy, or use existing libraries and create the APIs to stitch them all together, it is not clear. As you can see, we are walking different paths and we're comparing nodes, of course, and we will see how it will work out. Right now, it's not clear, but we need to try and see. In case of the context-oriented design, which is fully embraced by KMath and partially embraced by Multic, I won't go into detail, but they use a lot of it. At least they use extensions extensively. Solves a lot of problems with the operation binding and some problems of performance and specialization. Not all, of course, but a lot of them. And this is a tool we have in Kotlin that we do not have in Python or Java or a lot of other languages, or in C++, for example. The performance on GVM, I did not have any proofs here, but again, it's checked multiple times that the performance could be made pretty good on GVM, but it's not always predictable. So yeah, if we want consistent performance on all different GVMs, you need to check it. But I'm pretty sure that you can achieve very good performance. Not sure about Android because Android is another one. Android is not a GVM. Okay, I think I am out of time and out of breath. Maybe there are some questions from the auditory. Okay, I do not see any questions. Then let me just spend like 5 more minutes and show you the demonstration I prepared in Datalore. We're switching to the Datalore. Oops, something broken. Let me restart the page. Yeah, something broken probably in that. Okay, maybe no demonstration after all. Let's see. Aha, here it is. Here it is. Okay. let's see. The code is here. I hope you can see it well. I can probably increase the font. So yeah, like this. So you can see that another important thing in Kotlin, this notebook mode brings a lot of um, flexibility in working with Kotlin for data science and prototyping. And you see we're just loading those libraries. And then the example I showed you before about complex numbers, you can see it now and you can see the result. Here, the example of mixed algebra, matrix integration example, and another example is the example of interpolation. Interpolation is available. You can see here the result of interpolation, so it's more or less the same. Yeah, what is this? Something wrong here. Probably should be like this. Mm, this behavior is more or less expected. So the thing, if you are coming from the Python, it's also expected. So the difference is that in Python, it's pretty hard to work with functions. In Kotlin, since the functions are first-class citizen, it's much easier to work with the functions and not just with arrays. And in this case, we just created a function and then create an array using map function. It's not very effective because it by default it uses a list. But I believe in this case it's also optimized. So if it has a double arrays input, it will have a double arrays output. So it could be optimized automatically. Hey, something frozen. Oh, okay. Probably should close the presentation because it takes. Okay. For some reason, it doesn't work. You can. Actually, I wanted to show you one more example because that's very nice, and it was not in the presentation. Let me check if I make it work. Connection restored. Meanwhile, if there are any other questions, please do ask. If there are not, we will just wait to load it because I wanted to show you the example with what happens. I want to show you the actual example with automatic differentiation. But something is broken. Let me skip to this part. Yeah, here it is. Aha, here it is. Fit with automatic differentiation. Uh, it uses coroutines, so I need to enter run blocking phase and something. Okay. You can see that we generate data and we just sample the data using quite simple things, not unlike in Python. And then we can use map functions to apply functions to arrays. We do not need to do it in NumPy operations. We can use map operations directly. And then we create this symbolic expression like this one, which is automatically differentiated with a given processor. Here we use automatic differentiation from Commons Math, and it is available on GVM right now, but there is a pull request from Yaroslav which makes it available on other platforms as well. It's still not merged because it needs some work from my side mostly. And then without computing any derivatives, they are computed automatically. We just do this thing. We just say, yeah, just optimize this expression. And we just pass the optimizer, which could be different from different library. Again, it's an API. It's not implementation. And we pass initial parameters, and then we just get the result. And here how it looks like. So you can see those points here, and the points with years, and then you feed them, and they get result. You can get the detailed result with a chi-squared as well. So that's how it works. Pretty nice. Okay. So I hope it was not that boring. And if you have any other questions later, please ask them in either in Russian Telegram chats or in even better in Kotlin Slack in the mathematics channel, which is dedicated for mathematics. And of course, you can also ask not only me, but you can also ask people who develop Multic and other Kotlin libraries like Kotlin visualization libraries, Kotlin deep learning libraries, and other things as well. The community is growing fast. So, no questions? Okay, then we will end for today.